Hello everyone, my name is Sabinra. I am a freshman majoring in civil engineering from Paragon University. In this video, I will be explaining about trigonometric integrals, which is a subchapter within chapter 8, techniques of integration. The table of contents. First, we have definition of trigonometric integral. So what is trigonometric integral? Trigonometric integrals involve algebraic combinations of 6 basic trigonometric functions. In order to solve this type of integral efficiently, we must use trigonometric identities. And below are some of the most used trigonometric identities to integrate trigonometric integrals. We will use most of the identities right here in the next slide, so let's move on. First, we have products of powers of sine and cosine. So when an integral is in this form, which is integral of sine to the power of mx cosine to the power of nx dx, where m and n are non-negative integers, which means m and n are either 0 or positive. So when we face this situation, we must follow these procedures, which is divided into 3 cases. Case 1, where m is odd. Case 2, where m is even and n is odd. Case 3, if both m and n are even. Now, if you find this explanation right here a bit complicated and hard to remember, I found a more simple and short version, which is case 1. If power of sine is odd, we keep one factor of sine and we use Pythagorean identity of trigonometric function to change sine squared x to 1 minus cosine squared x. Case 2, if power of cosine is odd, we keep one factor of cosine and we use the Pythagorean identity of trigonometric function. This time we use it for cosine, so we change cosine squared x to 1 minus sine squared x. Case 3, if both m and n powers are even, we use half angle formula, which is sine squared x equal to 1 over 2 times 1 minus cosine 2x. For cosine, which is for cosine, you have cosine squared x equal to 1 over 2 multiply 1 plus cosine 2x. In a special case where both sine and cosine has odd powers, we pick one that will give power of 2 if possible. Now, if you understand what that means, I will explain it in the example, like in the next slide. Let's do some examples to test your understanding. Evaluate the following integrals. 1. A, we have integral of sine to the power of 3x cosine squared x dx. So if you recall from the last slides, which is case 1 where sine is odd, we keep one factor of sine and we transform sine squared x into 1 minus cosine squared x. We keep the last two the same. Now, in order to integrate this, we must let u equal to cosine x, so that the derivative of u will equal to minus sine x dx. When we do this, we'll be able to eliminate sine x from the integral, because sine x over minus sine x will be equal to minus 1, and what we have left are cosine. So in places where we have cosine, we replace it with u. So we will have a new form of function, which is 1 is 1 over 5 u to the power of 5, and u minus u squared is minus 1 over 3 times u to the power of 3 plus c. We plug u equal cosine x back in this equation. We will have 1 over 5 cosine to the power of 5x minus 1 over 3 cosine to the power of 3x plus c. Next example, B, we have the integral of cosine to the power of 5x dx. Now this one relates to case 2, which is when the power of cosine is odd, we keep one factor of cosine and we transform this cosine to the power of 4x into 1 minus sine squared x using trigonometric, using Pythagoras identity for trigonometric function. By then, we set u equal to sine x, so that our derivative of u will be equal to cosine x dx. We manipulate this equation right here for dx, so that we can use dx to plug it back into the last integral, and then we use u to plug in the odd integral where there is sine x. We will have a new form of integral, which is integral of 1 minus u squared to the power of 2 multiplied by cosine x and multiplied by 1 over cosine x du. From then on, we just have to do basic manipulation. This one right here will be equal to 1 minus 2 u to the power of 2 plus u to the power of 4 dx, and then we just do simple integration. 1 will be equal to the integral of 1 is u, the integral of minus 2 u squared will be equal to 2 over 3 multiplied by u to the power of 3, and u to the power of 4 will be equal to 1 over 5 times u to the power of 5 plus c. Then we plug sine x back into this function right here. We have sine x minus 2 over 3 sine to the power of 3x plus 1 over 5 times sine to the power of 5x plus c. Next example, c, integral of sine to the power of 2x cosine to the power of 4x dx. Moving on to the next part of the trigonometric integral, eliminating square roots. In order to solve trigonometric integrals inside the square root, we use half angle formula to eliminate the square root. And here are the half angle formula. Let's do an example. We see that there's a function within a square root, and we cannot integrate that. Therefore, we use half angle formula to transform it. Since our theta equal to 2x, therefore our function will be 1 plus cosine 4x equal to 2 cosine squared 2x. Now we replace the old function with the new function, which is integral from 0 to pi over 4 of square root 2 cosine squared 2x dx. Then we can eliminate square root from cosine squared 2x. We will have square root of 2 multiplied by cosine 2x dx. From then, this is just simple integration. The integral of cosine 2x is sine 2x over 2. Now, as this is a definite integral, we have to plug the value back into places where they have variables x. And when we finish that, we will get the answer, which is square root of 2 over 2. Next, we have products of sines and cosines. So to solve integral, we have these forms, which are integral of sine mx, sine nx dx, integral of sine mx, cosine nx dx, and lastly, integral of cosine mx, cosine nx dx. When we face this situation, we must use these identities below to transform the function, so that we'll get a function whose derivative is easily found. These are the three identities that will be used to integrate the function in this situation. So let's do some examples. Evaluate integral of sine 3x cosine 5x dx. Now, we use the identities in the last slide to transform sine 3x cosine. After that, if you calculate this equation right here, we get the answer, which is 1 over 4 cosine 2x minus 1 over 16 cosine 8x plus c. Next part, integrals of power of tangent x and secant x. We know that we've learned that already, that integral of secant squared x dx equal to tangent x plus c, and integral of tangent squared x equal to tangent x minus x plus c. However, to integrate tangent and secant with powers higher than 2, we use these identities, which are tangent squared x will be equal to secant squared x minus 1, and secant squared x will be equal to tangent squared x plus 1. We use these identities to integrate the integrals which have higher powers than 2. we also have to integrate by parts when necessary to reduce the higher powers to lower powers. To explain further, we change tangent squared x to secant squared x minus 1. We see that this integral right here cannot be integrated. Therefore, we will have to integrate it separately. We let u equal to tangent x, so that our derivative u will be equal to secant x dx. We manipulate it for dx. We have 1 over secant squared x du. We use that one to plug it back into the equation number 2. When we plug dx into the equation number 2, we'll be able to eliminate secant squared x from the integral. Therefore, we have only u to the power of 2x, u to the power of 2 left. And from then, just basic integration again, 1 over integral of u squared will be equal to 1 over 3 times u to the power of 3. And then we plug tangent x to places where there is u, we get this one right, this answer right here. And then we combine the answers from equation 1 and equation 2. We will have the answer, which is 1 over 3 tangent to the power of 3x minus tangent x plus c, tangent x plus constant c. To ensure that you understand, to strengthen your understanding of my explanation, I prepared a few exercises for us to practice. Without further ado, let's begin the first exercise. A, we have integral from 0 to pi over 2 of sine squared to theta, cosine to the power of 3 to theta, d theta. This time, we can recall from the last slide, when cosine is odd, we keep one factor of cosine and we transform cosine squared x, or this time cosine squared up to theta to 1 minus sine squared angle to theta, and then we can just let u equal to sine to theta so that our derivative u will be equal to 2 cosine 2 theta d theta. From then, we manipulate for d theta. We will get 1 over 2 cosine 2 theta du. Now we plug d theta into the old equation and u into places where there is sine. We will get integral of 0 to pi over 2 of u squared multiplied by factor of 1 minus u squared cosine 2 theta and 1 over 2 cosine 2 theta du. Then we can see clearly that we can eliminate cosine 2 theta from the integral. When we do that, we will have what we have left are and then from then on, we just do basic integration and we will get this answer right here. But it is not finished. We have to plug sine 2 theta into places where there is variable u. We will get when we replace u with sine theta, as this is a definite integral, we have to plug the value into the angles theta. And since sine to theta, and since sine pi equal to 0 and sine 0 is also equal to 0, we can conclude that the answer is 0. Next exercise, the integral of 0 to pi of the square root of factor 1 minus cosine 2x dx. This one we can recall from the last exercise, slides, that 1 minus cosine 2x is equal to 2 sine squared x using the half angle formula. From then, we can eliminate square root from the sine squared x, and then we integrate it, we will get minus square root of 2 cosine x. And since this is a definite integral, we have to plug the value in. So cosine of pi is equal to minus 1 and cosine of 0 is equal to 1. We get square root of 2 minus square root of 2, and we will get the answer, which is 2 square root of 2. Thank you, Professor, and thank you everyone for paying attention. Goodbye.